Hi all, this is Sundareshwari working as an assistant professor in the Department of Computer Science and Engineering. Today I am going to explain about the theory of computation, why we are going to study about theory of computation, what is the necessity of theory of computation. So basically, before learning about theory of computation, everyone should know about what is computation. So before learning about computation, you should know about mathematical sequences, mathematical operations like intersection, concatenation, etc. So what is computation? Computation is nothing but a sequence of mathematical operations. Which operations, like for example, what are not the mathematical operations that are going to be available, and a sequence of well-defined operations you should know. How many operations you should be performing, the fewer the better, which operations to be performed. So these are the things that you have to be clear and crisp knowledge about the computation. What you're going to study about in theory of computation is what is computable and what is not, what a computer can and cannot do. Are you trying to write a non-existing program, or basics of complexity theory and an algorithm analysis? You should have learned about it. And can you make your program more efficient? What you're going to study, the continuation is what is easy and what is difficult to compute, what is easy and what is hard for computers to do, is your cryptography safe, like this. These are the different metrics you should know about the computational theory before learning about theory of computation. So before learning about the in-depth of theory of computation, you should learn about the history and applications. These applications like analysis of algorithm, complexity theory, cryptography, compiler, circuit design, these are the areas which are going to concentrate more on theory of computation. So as we know about Alan Turing, he was the first invented the Turing machine and proved that there exist some unsolvable problems. In 1940s, these stored programs were built. In 1943, McCullers and Pitts invented the finite automaton. In 1956, the Klein invented regular expression and proved the equivalence of regular expression and finite automata. 1956, Chomsky defined the Chomsky's hierarchy, which organized the languages recognized by different automata into hierarchical classes. In 1959, Rabin and Scott introduced non-deterministic finite automata and proved its equivalence to deterministic finite automata. As we will be first learning about deterministic finite automata and non-deterministic finite automata, and we are also going to convert how a finite automata, a deterministic finite automata, into a non-deterministic finite automata. In 1956, 65, Hermantis and Steens defined the time complexity, and Hartman-Stearns defined the space complexity. In 1971, the Hook showed the first NP-complete problem, the safety problem also. In 1972, the Karp showed many other NP-completeness problems also. History of theory of computation. 1976, Diffie and Hellman defined the modern cryptography based on NP-complete problems. In 1956, Diffie and Hellman defined the modern cryptography based on NP-complete problems. In 1978, we all know in cryptography we have more clearly about RSA algorithm, that is Rivest, Samir and Adelman, who proposed this public key encryption scheme. Next, so these are the different history or history of theory of computation. The first one is, let's learn about the basics like alphabet and string. In theory of computation, alphabet is known as finite and non-empty set of symbols. For example, 0, 1 is a binary alphabet. Okay, here we can see that 0, 1 is a binary alphabet. Next, A, B, which similarly in theory of computation, uppercase, lowercase letters also plays a major role. So A to capital Z and small a to small z is an English alphabet. A string over an alphabet, this is called an sigma. It is the sequence of any number of symbols from sigma. So sigma is equal to 0, 1, which is also called as a binary alphabet, and capital A to capital Z is also called an English alphabet. And we also going to learn about some strings. These are the inputs that you are going to provide to the automatic machine. 0, 1, 1, 1, 0, 0 or 0, 1, 1, 0, the strings which we are going to form from 0 and 1. Okay. In alphabets, for example, you can provide these C80 or C80 and compute all the strings over the finite alphabet. So alphabet which may be a capital letter or small letter, these are called as the non-empty set of symbols which should be a finite alphabet. Next you are going to see about empty string. The empty string, it is denoted by epsilon. Okay, always you have to remember that epsilon is nothing but empty string which is containing no symbol. So epsilon is a string over any alphabet, which means that there is no input that is going to follow one alphabet to one input to another input, or one state to another state. Next, length. The length of the string x, it is denoted by length of x, which is number of positions of symbols in the string. Okay? Number of positions of symbols in the string, that is called the length of automata. For example, let sigma is equal to a, b to z. Length of automata will be 8. Length of computation will be 11. And length of epsilon will be 0. So x of I denotes the symbol, the ith position of a string x for 1 greater less than or equal to I, less than or equal to length of x. So x of I denotes the symbol in the ith position of a string x for the specific notations. Next we will be learning about string operations. The basic string operations like concatenation, substring and reversal. So as we know, concatenation is nothing but you are going to concatenate or you are going to join one string to another string. Next, the substring is, for example, you have madam, the word ada, ada is nothing but a substring of the particular string madam. Reversal, similarly, madam will be reversed with the same thing madam. Okay. Next, so first we will see about concatenation. Concatenation of strings x and y, it is denoted by x dot y or x space y, which indicates that the concatenation has been handled in a string z such that if z of I is equal to x of I for 1 less than or equal to I, less than or equal to length of x. So this is how a concatenation will be happening. For example, automata dot computation is equal to automata computation. If you specify this dot symbol, it will indicate that there is a concatenation will be happening. So concatenation of the strings are like this only. Okay. Next, substring. Let x and y be strings over an alphabet sigma. The string x is a substring of y if there exists the strings w and z over sigma such that y equal to w, x and z. Okay. For every string x, x will be a substring of x itself. For example, epsilon computation or substrings of computation. So you should be very careful that epsilon will be added in the substring also. Next, reversal. Let x be a string over an alphabet sigma. The reversal of the string x is denoted by x power r. For example, if x is epsilon means then x power r is also epsilon only. If a is in sigma, y is in sigma star, this is called clean closure, and x equal to ay, then x power r is equal to yr a. This is your reverse alphabet. This is how you will reverse the alphabet. Okay. This is how you will reverse the alphabet, right? Next, example of a reversal. So as you can see that a is reversed, right? Automata is reversed in the a will come here, d will come here, o like this, it will be reversed. Okay, this is how the reversal will be identified. Each step will be here. You see, each alphabet will be reversed, right? And finally you have to indicate the epsilon value. You have to always you have to remember the epsilon value, right? Next, sigma star. Sigma star is called as a clean closure, whereas if there is a plus symbol, it is called positive closure. In a sigma star, the set of strings created from any number 0 or 1 or etc. or symbol from it is denoted by sigma star. So that is sigma star is equal to union I equal to 0 infinity sigma power I. Okay, where sigma is equal to 0, 1. So you should always, if there is a, this is called a clean closure. If it is sigma power star is equal to clean closure, these clean closure should include epsilon. Whereas next you will see positive closure. In positive closure, you should not include epsilon, right? See, this is called positive closure. In positive closure, the set of strings created for at least one symbol, one or two, or in an alphabet, sigma is denoted by sigma plus. That is, sigma plus will be I equal to 1. Whereas sigma star you will be including from epsilon, whereas in plus, this is the positive closure, you will not be including epsilon. You can have a look over here. Whereas in the previous slide we saw there will be an epsilon symbol, whereas in the positive closure epsilon will not be included. Okay, so both epsilon stars, I mean sigma star and sigma plus, are finite sets. Next, a language. A language over an alphabet sigma, it is a set of strings over sigma. Okay, sigma is equal to 0, 1 will be the alphabet. So language is denoted by capital L, where epsilon to till, for example, the number of ones in the input. This is called the input symbol. Omega input symbol is even, so you will include epsilon because we have indicated the star, right? Next, so this is how languages are available. Next we will see about the operations available in the languages. So first one is complementation, union, intersection, concatenation, reversal and closure is available. First one is complementation. So let L be the language over the alphabet sigma. So the complementation of L, it is denoted by L per L dash, which indicates sigma star minus L, right? So we can see the input is the number of ones in U is always even, right? This is how complement of the number. For example, if you provide 0, the complement of 0 will be 1. For 1, it will be 0. So 0, 1 will be 1 and 0. So complementation will be working. Next, the union. So union is nothing but concatenation. We are going to combine language 1 and language 2. So let L1 and L2 be languages over the alphabet sigma, right? So the union of L1 and L2 is denoted by L1 union L2. So for the language exists in language 1 or L2. Okay. Here we can indicate that or is not necessary, or mean and is not necessary when you are going to combine in a union. Okay. Next, intersection. The intersection is and you are going to specify. If L1 and L2 languages over the alphabet sigma, the intersection of L1 and L2 is denoted by L1 intersection L2. So X is a language, X is a variable in the language L1. It should be present in both L1 and L2, right? See, you can see the example. X belongs to 0, 1, which means that X should begin with 0 and end with 0. Okay. Next, the concatenation, as we saw in the strings, the concatenation is nothing but you're going to combine two languages. If there is an input in L1 and W2 is in the input in L2, you're going to combine these two languages. That's called concatenation. Next, the reversal, as we have seen in the strings, the reversal of a number will be a substring. For example, 0, 0, 0 means 0, 0. You're going to repeat, right? It is called concatenation. Next is clean closure. As mentioned earlier, the clean closure will be indicated by the star symbol. We have to include the epsilon. Okay. Next, closure, positive closure. This is called positive closure. And this is how we do it. Okay. So these are the different basic knowledges you should know about before learning about epsilon closure, or you're going to learn about theory of computation. These are the things you should know. Okay, thank you so much.